Hello, and welcome to another lecture. So today we're going to be talking about winding numbers, and this is subsection 4.1.2 in the book. And sorry if my voice is a little hoarse today. There's something in the air. All right, so let's define winding numbers. So let gamma be a cycle, and p is some point not on the cycle. And we're going to define what we're going to call the winding number. We're going to write it like this, and of gamma and p, and we define it using this integral. Right, so it's the integral, and the 1 over 2 pi, that's just to make sure we get integers in the end, as you'll see. But basically, we're integrating 1 over z minus p, so we're going to be talking about the logarithm. So that's just by definition. You can just do that, right? And that's what we call the winding number of gamma around p, or sometimes the index of gamma with respect to p. And it will turn out, intuitively, what the winding number is, it's the number of times the gamma, as we're going around, remember gamma has an orientation, so it's going in some direction, and it's the number of times it goes around p, right? So number of times it winds around p. That's the geometric interpretation of what this is, but the definition is just, it's that integral, right? It's whatever that is. That's the definition of winding number. So for example, and why would we, why is it the number of times we wind around something? Well, let's think about some simple simple integrals. So for example, suppose that we have a unit circle. Let me maybe draw the there's this over here. We have the origin over here, right? And then unit circle, we're going around, and we're going in the counterclockwise direction, and we go once around, right? So this guy that parameterizes the unit circle, and if t is between 0 and 2 pi, we start over here, and then we go along the path until we end back where we started, right? So it goes around once around the unit circle. So we think this should go once around the origin in the counterclockwise direction. And if you actually compute this integral, if you explicitly just plug it into the definition, compute the thing, that's what you get, right? It's not hard to compute. So you got 1. It's precisely what we want, right? Let's change this a little bit. So instead of t as over here, I have e to the I 2t, right? Now what that does is it goes twice around, right? So I have my 0 over here. I go around once. Well, that's when t is a pi, right? I went back here, and then I go around again, right? So I've gone twice around 0. So I would expect that that winding number to be 2, right? I went twice around, right? And yes, it is 2, right? You just compute, you just plug it into the definition again and get 2, right? Now, what if instead of 2, I make it, minus 1, so e to the minus it. So what that does is it goes, I start out here, so this is where 0 is, right? Start at 1. And instead of going in the counterclockwise direction, I go in the clockwise direction, right? So I go opposite. So if I'm thinking of how many times did I go in the counterclockwise direction, well, I went exactly once in the other direction, so I'm going to think I went minus 1 times in the counterclockwise direction, or I went once in the clockwise direction. So that's why I'm getting minus 1 over here. And yeah, again, this is just by directly plugging into the definition of what the integral is. All right. So first, let's show that it's always an integer, right? So given any cycle at any point, this thing is an integer, right? And the point should, of course, not be on gamma, because otherwise I can't integrate, right? I have a singularity there. So the idea is, and plus, what would it mean for, how many times could it wind around P if P would be on the gamma? That clearly cannot be, right? So it is, we're definitely only thinking of P that are not on gamma. So we're looking at, the gamma is some compact set, and its complement has a bunch of components. For example, if it's a circle, it's the inside of the circle and the outside of the circle, right? And so n of gamma p is going to be an integer on each one of those components. That's basically what we want, right? Now, what's the idea of this proof? Is that, well, we're going to follow a branch of the log, so we're really going to be, changing, the log at different points, and then we just apply the fundamental theorem of calculus on little pieces of our path, and we'll notice that once we get back, we're going to be at some other, branch at that point of the log, and so it's going to be the argument is going to differ by some integer multiple of 2 pi. Right, and that's why, and we're dividing out by 2 pi I, right? So it's going to be an integer, right? So first, gamma is right? It's a cycle. So this is it can, it's equivalent to a bunch of it's a sum of a bunch of closed paths, right? So we could really just imagine that gamma is a single piecewise C1 closed path, right? If we prove it for that, then it's just n of little gamma, which would be one of these closed paths that it's a sum of, right? Then the n of the big gamma of the whole cycle, which is a sum of a bunch of these, would be just a sum of these integers. So if we prove it for a single path, we're good. All right, so we'll assume, without loss of generality, just assume that gamma is actually a single piecewise C1 closed path. All right, now gamma, I drew over here just a little piece of it, but it can be covered by finitely many disks, right? So I start somewhere, maybe this is D1, this is D2, this is D3, this is D4, this is D5, and so on. And I cover the entire curve like this, and none of these are supposed to contain P, right? So I pick small enough disks so that they don't contain P, because P is somewhere else. P is somewhere here, let's say, right? So if I'm covering the path and the P is not on the path, then I can choose these disks small enough so that they don't contain P. And they should cover gamma, and there should be finitely many of them, which is fine because gamma is compact, right? Now, the disks can also be chosen. This is, this is a bit of an exercise. It's kind of a problem in points-set topology that we can, or geometry of the plane, that we can do this so that there is a gamma is, it's again, right? It's gamma, you can think of it as a function from 0, 1, right, to C, right? So we can cut up the unit interval into finitely many pieces such that each, the entire bit of that piece always falls within one of the disks, where it really looks like the picture that we're doing, right? There's a little bit, you can't just sort of cover willy-nilly. You have to be a little bit careful, but you can do this. This is not hard. So that's an exercise that you can actually do it. So, that if you go from tj minus 1 to tj, you're in the jth disk, right? So if you start with it from t0 to t1, you're in the first disk. Then from t1 to T2, you're in the second disk, and so on, right? And there's only finitely many of these intervals, right? Subintervals. And we can do this because it's compact, right? Now, in each one of these disks, we choose a branch of the log, of z minus p, right? And we're going to call it L sub j if it's on the jth disk. And we can do this because p is not in the jth disk and d is star-like, right? So we know that we can choose some branch of the log on dj of this log, right? The log of z minus p, right? So z minus p is never 0 for z in the disk. So we can choose a branch of this log, and furthermore, what we're going to do is on that point where they overlap, then the tj, when we're at tj, we want the branch of the log on the dj be the same as the branch of the log on the next disk, right? So maybe let me draw this a little bit, right? So we have a disk over here and another disk over here, and I still want to keep with this, and we have our path is going like this, right? This is maybe, let's even start with d1, right? So we have we start over here. This is this is really gamma of t naught, but I'm just going to write t naught over here. And then over here, those were at t1, and maybe here there's a t2, and then goes on, right? And then maybe comes back and comes back over here. This is my d1. This is my d2, right? And what I want to choose the branches so that at this point the branch on d1 is the same branch as the branch, it has the same value at that point as the branch on D2. And I can always do that by picking the right branch, right? I can make them equal at one point, right? So I'm going to do that at that point where gamma is at T1, and so on. I can keep doing that. Then you start with an arbitrary branch, so we don't really care what L1 is. You just pick L1 to be arbitrary, and then you pick all the other LJs based on that, right? Okay, now it's a closed curve, right? So we start and end at the same point. Let's call it Z naught, right? And let's just compute this thing, right? So if we have the winding number of gamma around P, by definition, that's what it is, right? Now let's just plug in the definition of the path integral. Stick in let's make it into a Riemann integral, right? So we go from 0 to 1, right? Then we have the dz right over here becomes this thing, right? The gamma prime, and the 1 over 2 pi I stays out here. So this is what it is, right? Now, this thing I don't quite know yet how to compute, but this guy I'm going to be able to compute. Basically, what I do is I split it up into first an integral from t0 to t1, and then from t1 to t2, and then from t2 to t3, and so on, right? So I split it up into a bunch of smaller integrals. And the point is that over here, right, the gamma t for t between tj minus 1 to tj is always in the jth disk, and there I have a branch of log of z minus p, namely Lj, right? And I can just compute with the fundamental theorem of calculus what each one of these integrals is, and it's by fundamental theorem of calculus, that's what it is. It's the log, which is the antiderivative of this thing that's under the integral at the beginning and end point, and those are gamma of tj and gamma of tj minus 1, right? So I get this expression over here, right? some of these expressions, and you notice that these guys. This is a telescoping sum, right? So it's always minus the thing that comes in the next term, right? So the only things that once you write down what this is, the only things that survive are the first, like one of these from the first term and the last term, right? The only thing that survives is ln of z naught, right? Which was in this case it was the gamma 1, right? So it was this one from the n, because that doesn't get killed by a next term in the sum, because there is no next term in the sum. And also, there was nothing before L1, right? So the first negative guy also stays, right? So I get this expression over here, right? As that's the, maybe let me make it so it's not as dark. This expression over here, right? That's my, that's what this thing is. Now, maybe that would be hard to, tell exactly what it is, but one of the things that I can, just, I don't know exactly what branches they are. I mean, all this was kind of abstract, but they are branches of the log, right? And so as branches of the log, evaluated at the same point, z naught, there are many different branches of the log, but they all differ by a multiple of 2 pi I, right? And I'm dividing by 2 pi I, right? So, right, I mean, this is what it is, right? It's some, log of, absolute value of z naught. That's the real log. That's a given. That's always the same for any branch. But this argument, right? There's different values of the argument, but they all differ by a value of 2 pi. And so because of the I in there, I get 2 pi I, right? And so the difference is some multiple of 2 pi I. So if I divide by 2 pi I get an integer. And so we proved the proposition, proved the result. Okay, so the next result. So now we know that this is an integer valued function, right? So at every point, it is an integer. Now, the next thing that we're going to show is that if I look at the complement of gamma, that has a bunch of components. Now, the winding number is going to be, well, it's an integer. It's actually the same integer on the entire component, right? I mean, if I have, if I'm going around, if I have a circle, let's say, right, it goes around the inside of the circle. It goes around everything inside once, right? So the winding number of every point inside, it should be 1, right? And everything outside should be 0 because it doesn't go around anything that's outside the circle, right? And furthermore, there's going to be one. I'm just going to put it up on the slide here. There's a unique unbounded component because we have gamma is a compact set, so it's bounded. So if I go very far out, right, there's clearly just one unbounded component, topological component of the complement, and gamma doesn't go around any point there, right? So on the unbounded component, the winding number is 0. So that's the second part of this proposition. So basically, here's the idea, right? So if I have some curve like this, then I look at the different components, right? There's one component over here. There's another component over here. It sort of goes out here. There's another component over here, and then there's the unbounded component, which is everything outside, right? And you look at you compute this just by looking at it. So, or you can, but it's sort of what we're claiming. So over here, for example, right, we get 1. And that's because, well, we go around once. It doesn't really matter, what happens over here. Who cares? Because that doesn't go around any more times around these points. around the points over here, right? Now, let's say points over here, well, we go minus 2 times because we go, this way, right? That's, you can hopefully see how we went minus twice around. It doesn't really matter that we made a little loop over here. None of that, went around any of these, any of these points, right? If you think of it as the path as a rubber band, and now you'd put a little stick out here, put a nail here, right? And then the rubber band would shrink. It would, it would be precisely, something that went around twice, just, in a very tiny circle around the nail, right? If it was a really tight rubber band that just shrunk, right? And it doesn't really matter, what happened over here. All right, so that's the idea, right? And, out here, again, it doesn't go around at all. All right. So how do we do this? We actually are going to show that the winding number, thinking of it as a function of, so gamma is fixed, and thinking of it as a function of p, that this is a continuous function. All right, and it's a continuous function on this open set C minus gamma, right? So let's fix a point P naught in the complement of gamma, and let D be the integer, which is just the distance from P naught to gamma. So that's some positive number because gamma is compact, right? So we're at some point on the complement, so it's some positive distance away from gamma, right? So that's what we're gonna call D, right? Now, if we have, maybe let me draw this over here. So if we have, so we have, gamma is something over here, right? That's gamma, and then we have P naught over here. So the distance from gamma to P is D over 2. If we look at the disk of radius D over 2, right? Did I say D over 2 just why? This distance is D, sorry, right? I think I said D over 2 just a moment ago. If we look at a disk of radius D over 2 around P naught, right? And we take any point in this disk, then its distance to gamma is going to be at least D over 2, right? I mean, it can be further out, right? But maybe I could pick a point out here, but I can't get D over 2 away from P naught, which is D away from gamma, right? So I cannot be closer than D over 2, right? So I get so that's just triangle inequality, basically, right? That we get this inequality over here. That Z minus P is bigger than or equal to D over 2. Z minus P naught, right, is bigger than or equal to D. Right, that's going to be important as well, right? Now, let's give a name to the length of gamma, just so that I don't have to write down this. Let's just call it L, right, for length. All right, so now we're trying to do that, something is continuous. So let's look at the difference of this value between P and P naught. All right, now, if we write down the definitions over here and put it over a common denominator, right? So, it was one integral of, 1 over Z minus P naught and one integral of 1 over Z minus P. Let's just, sum it, do it as one integral. So that's this thing, and we have absolute values around it, right? So now we can estimate this. We can put the absolute values inside, so we get the path length measure over here, and we just put absolute value out here. The I disappears, right? And we're trying to estimate this integral, right? And that's an easy integral to estimate. We're gonna not worry about this. P naught minus P, actually. We're gonna worry about this, but a little bit later. So that's just a constant as far as the integral is concerned, right? It doesn't have Z in it, right? And then I have this Z minus P naught, right? That's bigger than or equal to D, right? Because That's how D was. That's by definition of what D was, right? Z is always on gamma, right? I mean, we're integrating by going around gamma, right? So Z minus P naught is at least D. Z minus P, right? Because P was in this disk, is at least D over 2, right? So if I bound these just by those constants, I will have a D squared over here, and the 2 will cancel, right? Because it's really, I have to, I bound it from above by 2 over D squared, right? So the 2 cancels, but that doesn't matter. It doesn't really matter. This is just some constant, right? L that just depends on the gamma, and D depends on P naught. So I'm, fixing a point P naught, but then P is just anything in this neighborhood around it, right? And so now if you look at this, right, I have this guy is bounded by this, right? That means that that this function is continuous at P naught, right? Because by choosing P to be sufficiently close to P naught, I can make this side as small as possible, right? So this is continuous, right? It's continuous at P naught, and P naught was an arbitrary point of the complement. So it's continuous on the entire C minus gamma. And it's continuous and integer valued, right? So it's constant. The only continuous functions that are integer are constants. Well, they're constant locally. So if we have multiple components, topological component, it could be a different constant on each component, right? So on each connected component of C minus gamma, it is constant, right? Because it's continuous and integer valued, right? So it can jump, of course, right? But that's what we saw in the picture, right? I mean, clearly, even if it was something very simple, it's a circle, right? It's the winding number is 1, and then suddenly as you go across the circle, it becomes 0, right? It can jump, right? But it can jump only at points of gamma, right? Where this thing is not defined. So wherever it is defined, it is continuous and it's locally constant, right? So it's constant on every component. Now let's prove the furthermore, right? That on the unbounded component, this is actually 0, right? So let's first take any point on the complement, right? And let's look at this the winding number over here. So we just bound it from above, right? I didn't quite write down the definition over here. I already put the absolute values inside, right? And we get this expression over here. Now, we can also bound that, right? So I'll put the L out here, right? That's just the length of the integral. And then this guy, well, I can just look at the distance of P to gamma, right? So I bound this entire integral by this expression over here, right? Now notice that if we're on the unbounded component, we can get as far away from gamma as we want. We're on the unbounded component, sort of what it means. We can just keep going towards infinity. So this distance can be arbitrarily large. So there are points on this component where this is arbitrarily large. Now we know already that this function, this winding number, is constant, right, on this component, right? And we know that it's arbitrarily small very far out, right? Because we're dividing by very large numbers, right? So that means it has to be 0, right? That's the only way that this can happen, right? So we know we can pick this thing to be arbitrarily small, and it's constant on this component, therefore it's 0, right? So that's the conclusion. All right. So those are the basic results about winding numbers. So let's just give a couple of, maybe not even the results, really sort of couple of computations that are left as an exercise, but these computations are used all the time. And we won't really bother with them, after this, we're just going to assume that's what these are. So if we have a circle, right? So we have the boundary of a disk centered at P of radius r, and we look at the winding number around this circle, and we're orienting everything counterclockwise unless specified otherwise. So if Z is not in the closed disk, right? So it can't be on the boundary. That would make no sense, right? But if it's not in the disk, it's outside the disk, then the winding number is 0, and it is 1 if it is inside the disk. And I claim this is it's sort of a trivial exercise, but it's good to go through it and figure out why that is true. Right. Once you see it, it's sort of obvious. There's not much that you have to compute. Right. I mean, we've actually done the entire computation that you need to do. Now, another place where this comes up commonly is as an annulus. So if we have an annulus, right, it's around some point, and we have two circles, and I'm going to orient the outside one positively and the inside one negatively, then basically what we're going to claim is that the winding number is going to be 0 here, 1 here, and 0 here, right? And it's really just by adding things up. You use the previous exercise, right? So that's if we're in the inside circle, then it's 0. If we're between the circles, it's 1. And if we're outside, it's 0, right? So again, those are just, that's just going from the previous exercise, right? So, all right. So those are winding numbers. And so cool. See you next time.